welcome also from my side. As Georg already announced, I'm working in the OpenMP community and also in the MPI community for quite some time now. I'm working mostly on tools for MPI, OpenMP, correctness tools, and also performance tools. But the work I'm talking about today is actually more towards the application space, and the idea is to get more scalability into applications so that we can actually scale up to exascale, if you want to use this buzzword. So what is it about? The initial idea came shortly after Josef Schuchert published a paper at RWTH, where he tried to build up an application that uses tasks, OpenMP tasks, and port this to distributed memory, and then integrate MPI communication into OpenMP tasking. The issue that he pointed out in his paper was that OpenMP, because of some weak guarantees in the specification, is not really suitable to execute asynchronous communication and allow or guarantee to get progress all the time. So in different configurations that he tried out, he ran into deadlocks, and these deadlocks were caused because of weak guarantees in the OpenMP specification. What I'm talking about today is basically based on a paper that I submitted to EuroMPI 20, and where he actually also published a similar proposal to do really asynchronous communication in MPI and get a notification from MPI when the communication is done. And what I will show today is how you can integrate OpenMP tasks and OpenMP task dependencies with this kind of asynchronous API communication. So first, for those who are not so familiar with OpenMP tasking and task dependencies, what are OpenMP tasks and how do OpenMP task dependencies work? There are mainly three OpenMP constructs that are used to generate tasks and that accept the dependence clause to express dependencies between different parts of work. The task and the target construct actually generate tasks. The task wait construct is a synchronization construct to terminate or to guarantee that certain tasks have finished. The task wait construct, since OpenMP 5, I think, also accepts the dependence clause, which means you can actually wait for specific tasks that share this the dependency. Other tasks are not necessarily finished when you pass such a task wait with dependence. The dependence that you can declare there is based on variables and the address of the variable you pass in to the depend clause. And then you can have different dependencies: independence, out dependence. Out dependence is always also independence. That's the reason why the description in the specification basically makes a difference between out and in-out dependence. Then something quite new is mutex in-out set, which declares mutual exclusion between tasks that have the same dependence, but also ordering with all other dependence classes. And then there is in-out set, which is a weird thing, which is basically in two, which means you can have one set of independences, so all these tasks can execute in parallel. And then if you have in-out set then that's basically the same thing. They are another set of tasks that can execute concurrently, and then you can have another set of independencies. So it's a weird thing. I never understood the use case for that, but that's a different topic. So it's basically the same as in. So how would you use tasks to parallelize a code? The example that I'm using here is Block-synchronous decomposition. The idea there is we have a huge matrix. We partition the matrix into some blocks, and then we want to factorize this matrix. And the algorithm is that you iterate in smaller and smaller parts until you have the complete matrix factorized. And the code for this is basically this larger for loop that iterates over the smaller partitions. So basically the layers that I showed there. And then you have 4 steps. The first is the red function that you apply to the top left block in this triangular blocking scheme. Then you apply the next kernel, which all those are BLAS functions or LAPA functions. So you throw in your matrix coordinates pointers, and then you get the result into one of the blocks. So, so the first kernel is the red one. Then we iterate over the column. That's the next for loop. Then we iterate over the diagonal to calculate those things. And then we iterate over all the remaining blocks to calculate a matrix multiplication. In the small example that fits into onto the slide, it's not so obvious that at the end the matrix multiplication kernels are the dominating number of kernels, because if you scale that at large, they are O of n square, while the other kernels are only O of n in a number of tasks. So if we do naive tasking for this serial code, then we would introduce tasks around all those math kernels. This generates OpenMP tasks that can be executed in theory or in parallel. And then we need to make sure that we still meet the dependencies between those tasks. And the naive approach is to throw in tasking barriers, which is a task weight. This gives us a correct result, but it does not scale very well, because we still have blocking synchronization in there. And some threads will always need to wait until all the tasks are completed before we can continue in the execution. So the better approach for scalability there is to actually declare the dependencies between the tasks, so that you can reach the maximum available concurrency. And the dependency here is described with a depend clause, and depend in out A of I is basically the block that we put in here, and it's also the first argument of this math function. The first argument of all the math functions is underlined, because that are the in-out arguments for the functions, and the other arguments are just input arguments. And with this information, we also understand, okay, we have independence on the second and third argument, and we have an in-out dependence on the first argument. So this dependence now introduces these dependence arcs, which tell the OpenMP runtime in which ordering all the tasks can be executed, and we can reach basically the maximum concurrency for this kind of algorithm. If we look at the resulting dependence tree and how the different tasks depend on each other, then we get a graph like this for this small program size. And then, of course, if you scale it up, and a typical execution would probably generate, typically do a blocking of probably 200 or 500 blocks in each dimension. And then we get, of course, way more tasks, and the dependence tree gets really huge. Now, the goal was to not have this code executed on a single node or in a single process. The goal was to actually distribute the work onto different processes. And for this, we distribute the work based on two-dimensional cyclic block distribution. And so basically the lower left corner shows us the distribution scheme, and the whole matrix is basically distributed along the scheme. And this again can be scaled up to more than 4 processes. It's just the toy example that fits onto the slide. So the blocks are distributed to the processes. The different processes are assigned the work or the math kernels to execute the calculation for the different processes. And it means as if one of the computations needs input from other processes, we need to exchange the data, and the dependent task needs to send the data over to the process to calculate this next block, or to perform this next kernel. So looking at the task tree again, I highlighted the arrows, the dependence arrows that actually express dependencies between the nodes with red arrows. And as you can see, there are quite some arrows now that are red, which means we need to transfer data. And as soon as the data is there, we can actually execute this task. And so what we can do there is basically, as soon as this first task is executed, we send the information for the result of the calculation to the other node that needs to do the next kernel. And this can be basically expressed as we have a send task that depends on the calculating task. Then on the receiver side, we have a receiving task. And as soon as the data is there, we can execute the next task. So what we want to express there can now with OpenMP 5 be implemented using detachable tasks. The idea of detachable tasks is you have a detach clause that you can put on a task, and the detachable task means the execution of the task finishes, but it's not completed. So the runtime knows, okay, although the code of the task is executed, there's something missing, something outstanding that is missing to actually complete a task. And our dependencies depend on the completion of the task. It's not sufficient to finish the execution of the task. The task also needs to be marked as completed. So what I noted here as a high-level notion is that we detach and depend on the request, which is the request that we pass into MPI. It's not the actual syntax, it just tries to bring over the idea. So we depend on the request to be finished, and as soon as MPI tells us the request is done, we can complete the task, and then everything resolves by itself. So how can we integrate OpenMP detached tasks with MPI communication? The point that we made in the paper is that we cannot do this with today's MPI. We need a new feature in MPI which somehow tells us, okay, now the communication is completed, and we get actually a callback from MPI that says, okay, now the communication is completed, and it's basically the opposite of polling and testing for the completion of the communication. With this callback, we can then tell OpenMP, okay, now the communication is completed, and now the task can complete. So we have this new function. In the paper, we call it MPI detach. Now, since there are a couple of years gone, we are still in the process of standardizing that in the MPI forum. There is a proposal now. It's called MPI continuation. So if you look for this feature in probably 2 or 3 years, when MPI 5 is published, then you should find something that is called MPI continuations, and it basically works like this. Just the interface is a bit different. So what we pass in there is we pass in the request that we get from I send, I receive. We pass in there the callback, and we pass in there some void pointer that we can then that we then get back into the as an argument to the callback function. And the semantic is we pass back the request to the MPI library, and as soon as the MPI library knows, okay, the request is done, we get notified, okay, the communication is completed, so we received the data. Just to be similar with all the other test and wait functions, we also defined something similar to wait all. We also have something similar to wait any, wait some. The main difference is that we need different signature for the callback function. So in this case, we have detached statuses function. Okay, there is an error, so this should be this type signature. So one thing that I need to know there is we had to introduce different functions for the case where we actually want to get the status, and for the case where we are not interested in the status, because now the calling direction is the opposite, and we cannot signal MPI that we don't want the status by passing in MPI statuses ignore. We need to tell MPI in advance that we actually are not interested, and so we pass in a different callback function. One thing that makes it a bit complicated is, and that's similar to this weak guarantee that OpenMP had for the execution of tasks. Now we are in a part where MPI provides weak guarantees about the progress of communication. And the background for this weak guarantees that MPI provides there is that dependent on the implementation, MPI might only be able to actually make progress on communication while the MPI library is active. That means while an MPI function is executed. Now, in our execution model with this asynchronous completion of communication, we basically need MPI to make progress in the background because we don't have any guarantee that we will call MPI while we are waiting for the progress to be made. So what we propose there is actually a new function, an MPI progress function, which only has the purpose to actually do the progress. And if MPI detects, okay, communication is completed, there it has the chance to actually call the callback and signal us that the communication is done. This is something that could be integrated into a polling service, and OMS2 actually has such polling service, which is integrated with the OMS tasking runtime. And we did some experiments there. It works quite well. For our prototype, we actually start a background thread which calls this this progress function in a loop with some sleeps in between, so that we don't overload the core and leave the core basically for the application. Now to the actual usage, how you can use this interface in the application. So what I had before was I had the request up here. Now now I have this event handle, which is the actual OpenMP symbol that is used here. This event handle is passed in as the void pointer data object to the detached function. And then as soon as the communication is completed, MPI will call the OpenMP fulfill event function, which is the OpenMP function that signals the runtime that the event is completed. This is the argument here, and that means as soon as MPI calls this fulfill event function, the task is completed, the dependence is resolved, and then we can actually execute the task that is dependent on this communication. This is what we integrated into the Koleski code, and now the Koleski code basically looks more or less like this. So we have some tasks that have an out dependence on communication tasks that send over the data. The receive tasks receive the data, and then we have other tasks like the gem tasks that depend on the receive task. So using this approach, we now can express, or we can map the task dependence tree that we have on a single node to a distributed layout. Basically move the tasks, not really move the task between the nodes, so we don't have active load balancing, but just by creating the tasks on the different nodes, adding communication, we can reach a distributed dependence tree and execute the code in a distributed fashion. What I will show in the next slide is performance comparison of a more or less block-synchronous execution, which is more or less like this here. So we have just one task that executes the MPI communication, sends the data over, and then all the other tasks are dependent on this on the send-receive task. So this more or less introduces a global synchronization at some point, and this is really a fine-grained communication scheme, and there are some variants that are there to compare the different approaches. That some of them were shown already by Josef Schuchert in a paper, and we just reproduced this measurement for the comparison. So what is highlighted here is the measurement for the implementation that we proposed there with a detached communication. On the left, that's the block-synchronous synchronization, how you could implement it with today's MPI or with MPI available 3 years ago, and Clang 3 years ago. And so what you can see is that the scalability, when you this is not yet the scalability plot. This is just a comparison how this scales when we do different configurations of MPI processes versus OpenMP threads, and basically how can we fill a single node with different combinations of tasks and processes. The main reason why I showed this here is that you can actually see the NUMA effect, because the first column in each configuration is filling the whole node with threads and only executing one process. So you see the NUMA effect. Then on our system that I use there, we have also subNUMA clustering inside of the socket. That's the reason why you see a bit more computation time for the same amount of work in a two-process configuration. And then as soon as we limit the process to a specific NUMA domain, the curve is more or less flat. And then the yellow overhead is the overhead coming from the communication. So now I show the scaling plot, which is strong scaling from one node to 32 nodes, always with executing with 12 threads, because 12 threads was the configuration where we have the least overhead in a node scaling experiment. And what we see now is that the overhead for 4 processes is the smallest across all the different configurations. And then also scaling up, we basically beat most other configurations. Only for the largest scaling, the OMS configuration, which does some task yield tricks from Josef Schuchert's paper, outperforms our solution a bit. But this is an implementation that is not portable. This is the configuration that actually leads to deadlocks if you execute it with a different runtime than the OMS runtime. Okay, so looking at this scalability behavior, I always click the wrong button. Looking at the scalability behavior, I was actually curious, where does the scalability issue come from? And I wanted to do some performance analysis. The problem there is if you work in a top edge of what the different MPI, OpenMP specifications provide you, or the implementations provide you, then the tool support is not that great. So I actually had to do some tricks to actually get some performance results. And then I started to work in a POP project and came into contact with the performance model factors defined from BSC. And I developed a tool to collect the performance model factors on the fly, also for hybrid measurements. And because I implemented it new, I could fit in all the new features I needed for this performance study. So I will first give a brief introduction on what the performance model factors are. because I think they are a great vehicle to understand scalability of parallel codes. The idea there is to break down parallel efficiency into three components, which are actual factors. And if you multiply these factors, then you get to the parallel efficiency up here. So the nodes here, you can multiply them, you get to this metric, and then the nodes down here, you can multiply them, then you get to this metric. So what are these basic factors? One is load balance, which means it describes the balance, how good the work is distributed between the parallel executors. Serialization efficiency can also be understood as temporal load balance, or it tells you how much cyclic dependencies you have between the different executors. So if one process needs to wait for the other, and then in the next step another process needs to wait for the third or for the first executor, then this is serialization efficiency. And then transfer efficiency expresses how much of the waiting time is caused by transfer, and transfer can be MPI communication, transfer can be synchronization between threads, overhead coming from synchronization between threads, and all that stuff. If you do performance reports based on these metrics, then you would get a scaling table that could look like this. Metrics are, well, there is basically no parallel efficiency loss for serial execution, where there is still some performance loss just by having the constructs in there, or just by having the MPI calls in there. Also, you execute with one process, but then as soon as you go into parallel, you lose parallel efficiency, and that's marked as the red bar here. And then if you look into the details, then actually the parallel efficiency is not caused by MPI, but in this case, performance loss is caused by threading. Brief formal definition of what the different what the three basic metrics are. Load balance is calculated by useful time, and useful time is basically time in the code, or you can also call it time outside of parallel runtime, so time outside of MPI, time outside of OpenMP. So average useful time divided by max useful time, that's how the load balance is calculated. And one probably needs to think about it one or two times, and then at some point it makes sense. So it took me quite some time to completely understand the three performance model factors, but then they really make sense. So load balance is the first part, and it's also highlighted down here. Then the next part is serial efficiency. This is the waiting time that the different processes need to wait, other than caused by load imbalance. And then the third metric is the transfer efficiency. That's basically the time that all processes more or less need to wait. And this can only be optimized by going to faster network or less latency in thread synchronization, for example. Or by doing less frequent communication, by doing less frequent synchronization in a threading code. Okay, so then the question was how do we measure this the metrics? Useful time is basically you need to measure time in MPI and OpenMP code. So there it's quite clear. Okay, just whenever you enter a parallel runtime, you stop the timer. Whenever you exit the parallel runtime, you start the timer. Real time is also quite clear. Real time is the time you observe for the overall execution. The interesting part for this work was how can we measure the ideal runtime? And the ideal runtime is the idea there is it's the time spent or the time you would need for the same execution if you run this on an ideal machine, which has zero latency, which has basically infinite bandwidth. And zero latency both for MPI communication or for OpenMP synchronization. Also scheduling threads, scheduling tasks should be a no time thing. So basically what we want there is we want to measure the useful or the application code execution time on the critical path. Because we assume we don't need to pay for whatever synchronization cost is. And there I showed, okay, you can actually calculate this metric on the fly. This was something that some people working on critical path analysis told me, no, for critical path analysis, you always need to do forward-backward analysis. You need to follow the critical path backward to calculate this. But the point is, we don't want to explicitly know what is the critical path. We are actually only interested in the useful time on the critical path. And so this is what we can actually do at runtime. And then we have the metric at the end of the execution, and we can report all the metrics at the end. And there's also some detail in the paper. We can actually split and break down this information by following different critical paths. One inside of the process, one that also takes care of MPI communication, and then separate time or the delay caused by MPI from delay caused by OpenMP. So here are traces that I collected for the execution using some tricks with SCORP, and then showing the result in VAMP here. What you can see is synchronization time is this light blue or cyan. This is time spent in OpenMP synchronization. So there, the worker threads wait for the main thread to do the MPI communication. What we have on the top is a block-synchronous execution, where all the threads for the next phase need to wait for the MPI communication to be completed. And only when all the data is there, the next phase of, or the next chunk of tasks can execute. The dark blue parts are actual execution of the different mask kernels, and what we see in red is MPI communication. On the bottom, that's the completely asynchronous execution using detached tasks and the MPI detached communication. What we can also see in this plot is we have an extra thread that takes care of completing all the MPI communication in the background and sending or telling the OpenMP part of the code that MPI communication is done, releasing the task dependencies. So this is a thread that is spawned extra. For the measurement, we do not request an extra core for this thread. This thread just runs in a CPU set assigned to the process. So this thread will always run in parallel with one of the worker threads of the application on one of the cores. Nevertheless, we get significantly shorter execution time for this small scale example, and I use the small scale example just to actually keep the trace small and to show some traces here. Now, based on this tool, identifying the critical path, calculating the metrics on the critical path, and calculating the performance model factors on the fly. I did the measurement with two different codes. One, first a block-synchronous code. Again, down here, we see the trace. But the interesting part is that already with 4 MPI processes, we spend basically 5 to 7% of the time on the critical path in MPI communication. So this is MPI communication that blocks us from making progress in a calculation, and that is not hidden with computation overhead. And then, the scalability is quite weak. So here we have a parallel efficiency that is below 20%. What you also see is a breakdown in how much is caused by the OpenMP part of the application. So here we have a parallel efficiency of almost 100%, while the MPI part is a weak part. And then down here, we also see the scalability of this strong scaling experiment. And we see that the execution time for the 32 processes actually goes up from 32 nodes, goes up from 16 nodes. Yes?
Maybe a question. Sorry if I didn't follow and you already answered this. How many of those threads communicates? Just one or all of them? So the question was how many of the threads communicate. In this block-synchronous code, there's actually it basically represents an execution where only one thread communicates, because there's only one communication task that does the communication. So all the communication is wrapped into one task. We have independencies for this task, and then we have our dependence from this task. That's causing the synchronization here, and that's also the reason why when you look at the trace here, then you see MPI communication only on a single thread. In the next configuration, we now have MPI communication from whenever the data is ready. Then there is some task that will execute the MPI communication, and now we really have completely multi-threaded MPI communication. The MPI communication is done in the background. It's completed by the extra threads that we see as a more or less white line in here. But what we see now in this hybrid breakdown is up to 32 processes or
8 nodes, we actually get significant overlap of communication and computation. And only if we scale up higher, then we actually get impact from MPI communication, and we cannot hide the MPI communication by computation. This is something where if you would probably put in more effort in optimizing the communication pattern there, you could probably avoid part of the communication and optimize that by just redistributing the work. I mean, that's not a production code, so it was not worth investing the effort there. Nevertheless, we see in a scaling curve that even for 128 processes, we still get a bit faster. Looking at the plot up here, we actually see that this is just by the additionally introduced tasks, the additional introduced task dependencies between different tasks. We actually introduce also OpenMP overhead. This is something that we can see from the plots here, and then yeah, still most of the performance loss is still caused by MPI. So this gives a bit more details of where this parallel runtime overhead comes from, compared to the measurement we had in the initial paper, where we just could measure, okay, this is the time that we measure for the MPI, for the mask kernels, which is the blue bar, and everything else is parallel runtime. And now we have actually a breakdown which tells us, okay, the overhead is caused by MPI communication, so we should focus on MPI communication to actually reduce this more. So to conclude the talk, what I showed today is a slim extension of MPI with 7 new functions for MPI. And this provides us really asynchronous MPI communication compared to non-blocking MPI communication, which we have today. This is an MPI proposal, which hopefully will go into MPI 5. We will not make it for MPI 4.1 because there basically the roadmap is already rolled out, and that's not achievable. I presented how this can be integrated with OpenMP tasks. There is a prototype of this MPI part available, done as an PMPI wrapper. You can download this from GitHub, use it. It's just 350 lines of code, so you can actually review it, integrate it into your application if you want it. So you can use this already now. Also, it's not in the MPI standard there yet. It's portable between the different MPI implementations this way, so you can use it with any of OpenMP MPI, OpenMPI, MPitch, or Intel MPI, which has to do with all of those. Then we did a performance study based on this implementation. The performance study can be downloaded, or the code for this performance study is available on GitHub. Yeah, one thing that we missed during the implementation of this work is when you see an MPI request, you don't know whether it's a persistent request or not, which has some implications for what you need to do with MPI wait, or what we need to do with the detached, because for persistent requests, you should not reset the request handle to null. For the other requests, you should reset it to null. So this is something where the MPI standard also might give some additional, or might need some additional API to actually provide this information. And then at the end, I showed you the hybrid performance model factors. to actually understand scalability of codes. And this is also something that I hope to release within the next. I mean, the code is already there. I just improved this by a lot, and I hope to make this tool also available within the next couple of months, and then that will also go to GitHub. Okay, and with that, thanks for your attention, and I'm open for any questions.
All right, thanks a lot. Are there any questions either from here in the room, or if you're in Zoom, have a question, just unmute yourself. Let's do that.
Why is these? So when you compared the two approaches with the performance studies, the load imbalance for OpenMP raised for the hybrid approach, which was not visible for the other approach. So the dark blue, dark red is here. You see some line getting bigger with 128 threads. So where's the load imbalance introduced by OpenMP? I mean, yeah.
I mean, the load imbalance is basically always a result of runtime decisions made by the runtime.
Okay, so that's not controllable.
You cannot control how the runtime decides which thread will actually execute a different task.
I think what you want to know is why doesn't it show up in the other one here? So why the difference? Because it's the same workload for the OpenMP regions, right?
But I mean, here you have clear phases where the execution is blocked. But I mean, at the end, I don't really know why.
Okay, yeah, maybe I just didn't get the full meaning of these factors that come into the parallel efficiency in the end of these. I mean, also this serial efficiency. Here you see much larger bars compared to the other one, which somehow means that they are, yeah. I mean, they are diverting more in the second case.
Yeah.
Maybe can you show the time once again? So between those two, so this is block-synchronous, and then when you and then the asynchronous case. But the time doesn't change.
I think the top right figure doesn't change between the two slides.
So that would be also
interesting. So these are on the left. That's basically the block-synchronous code, and that's the detached code. That just shows the comparison from the paper.
And the dark blue is what you use useful time, and
right.
The other one is the parallel region time.
Right.
Yeah. Okay.
One thing that I think didn't quite understand is what's the difference between this detach clause that you have introduced and used as a basis for this work, and just building a task which does a blocking receive and just waits until the data has been received, and then the task ends and the dependencies fulfill. If the MPI library internally does some spin waiting anyway, whether I do the spin waiting in the task or within the MPI library, doesn't it make a difference?
Right, when you do MPI receive in the task, so that's basically the probably even more block-synchronous version to that one. I'm not sure. No, probably that comes close to this code. But what I start with the detached clause is non-blocking communication. So I just initiate communication, and in the meantime I can do computation. So with the detached, probably I should go back to the code.
right, with a detached clause and an MPI detached. So I pass back the request handle to MPI, and then the execution of the task completes. That means the OpenMP runtime at that point can schedule a different task. I mean, the assumption there is some other task that can be scheduled that is not dependent on this communication task.
But there should always be a lot of tasks that should be able to schedule. Because if that's not the case, everybody's waiting for MPI, which is not good. So if there are always lots of tasks and only a few tasks are actually producing MPI messages that are other tasks depend on, there should always be a task waiting. Okay, so does it make that much of a difference whether this task waits or not?
Yes.
So I mean, I can only if there's a dependency like here to something with buff, right? So that has a dependency on receive buff. So it can only run if receive buff is actually here. And that can happen under either if I use plain receive in the first task. That happens when this task ends. So when the blocking receive ends, then the dependency is fulfilled. But in this code, the task also ends when the non-blocking receive is fulfilled.
Yeah, so it ends earlier. So in this case, the execution of the task ends as soon as I just said MPI just received this data, and I can do some other work. If I do MPI receive, I'm blocking the task. That means I'm blocking the thread. No other task can execute on this thread, and I'm just busy waiting and blocking a full core, waiting for MPI.
Okay.
And with I receive and detach, I release the core, can do something other on this core, and then as soon as MPI tells me, okay, the data is here, all the tasks that are depending on the received task are released, and they can be scheduled as well. That was basically here. So that's an implementation choice. In my implementation, I need this background thread to do the progress, because I have no control about the MPI implementation, what is done there. If this is integrated into MPI, then what the implementation could do is in the ISend, the buffer is passed to the NIC, or the address for this buffer is passed to the NIC. This is introduced. This is put into a queue in the hardware. At some point, the network card will do the direct memory copy from the local memory to this other node into memory, put it to the hardware, and then at some point, the network card which received the buffer and which had this receive initiated by an iReceive will find, okay, I received this message that I was waiting for, and yeah, it completely depends on the hardware or the hardware features that are available there. In theory, the hardware could trigger an interrupt. The interrupt knows, okay, this is something I was waiting for, and I actually need to do this callback. So the callback could actually come from the interrupt handler, and so this can really be executed in background, or the implementation still needs a progress thread, a shepherd thread, which takes care of the communication and which will do the callback notification.
So the point is not to free a slot in the waiting queue. The point is to free a thread and to offload the progress to your helper thread that does the progress in the background in a resource efficient way, not polling all the time or not calling MPI test all the time, but doing it like in a resource efficient way. That's the difference. If I just do MPI receive, I'm blocking this task, so I'm blocking the whole thread that's currently executing the task. That's the problem. Okay.
I mean, that was basically the first approach that Josef presented at IWOM. There, he actually, I don't think I have the actual
code here. But what I did there, instead of having this detached call here, he had a test loop. And as soon as long as the request is not completed, he did a task yield to basically tell the OpenMP runtime, try to schedule a task here, and then if there is a task that could be executed, and if there is no task, then we would just continue the while loop.
And that means if you yield and it doesn't come back anytime soon because the tasks you're just now executing are very heavy, then it takes a long time until you come back to the next test. Yeah.
But the more severe problem there is that the task yield has a quite weak guarantee from the OpenMP spec, so it could be a no-op. That's a valid implementation for task yield, and it actually can cause deadlocks because we are polling. We don't give up the thread, and if there are multiple threads waiting for the MPI communication in this task yield loop, then at some point you don't have any thread to actually make progress and release some of the tasks.
Okay.
And yeah, and the other, and I think that's actually something that I had in one of the slides at the end. Oh, okay, I can't get to the slide. It's the hidden slide probably. Oh yeah, that's actually the code pattern. So test and then while not received, task yield and test again. So one choice is task yield can be a no. That means no task is scheduled there. So potentially none of the send threads will be scheduled, so that no data is sent and we have a receive deadlock effectively. Because effectively this becomes just an MPI wait. And the other choice of OpenMP is the OpenMP implementation can choose to schedule a task immediately. That happens, for example, in the LVM and Intel runtime as soon as the task queue fills up, and then the task is scheduled immediately. And that means with bad luck, the send task either is not yet created, or so it's not at all in task queue, or it is created but will not be scheduled because the received task is scheduled first. And so there's a lot of potential to get into deadlock situations. And with a detached approach, there is no way to get into deadlocks.
Okay, any more questions? Nothing from Zoom, so then let's thank our speaker again. Thanks a lot.
Okay, and we'll show the links again. Yeah, thanks for inviting me.
Okay, so see you next time. Next seminar is on April 18th.